Thank you very much. Well, good morning. I am Angus, and I'm here to give you an inside look at Rust in the space industry. And as a bonus, in 25 minutes' time, you will be able to model 13 billion years of time, that's all of it, with femtosecond precision in 7 astronomical timescales. No background in astrophysics required. It's not rocket science. We are going to see how Rust is powering the next generation of space mission simulators, because to cross the final frontier, you need to know where it is and how much fuel you're going to need to get there. So for the people at the back, I know the slides can be a bit hard to see in this room, but you can already find them on the Discord channel for this talk. So feel free to... Hey! Feel free to follow along if they either freeze or they're too small to see. First, though, let me release an elephant into the room by telling you that I'm a software engineer, not a doctor. I don't have any formal education in astrophysics, and in my spare time, I teach Rust on my site, howtocodeit.com. So if you're wondering what authority I have to be talking to you about space mission simulators, don't worry, I had the same question. When I was approached for this project, the lead told me they just need skilled Rust engineers. But I thought, better safe than sorry. I should ask, are you sure I won't need a background in astrodynamics? And he said, yes. And that was a lie. So the last year has been quite uncomfortable for me, not because astrodynamics is surprisingly, unusually complex, not any more than you'd expect, but because historical astrodynamics code is often spectacular in its accidental complexity. So to show you how Rust is bringing balance to the force, let's establish some context. I am a core team member for Ephemerista, which is a new open source space mission simulator. It is wholly funded by the European Space Agency and maintained by the Libri Space Foundation, which is a non-profit for the promotion of open source software and hardware in space. And when complete, Ephemerista will include GUI mission planning and analysis tools, a Python API tailored to flight dynamics engineers and mission analysts, and pluggable integrations with existing tools, all backed by the thing I'm going to talk to you about today, LOX, an ergodynamic Rust astrodynamics library which is rapidly approaching V1. And an astrodynamics library has a lot of responsibilities. Like, we would like to know how to get from A to B, where A and B move in 3 dimensions and may be so massive that they alter the flow of time itself. And getting from A to B takes a certain amount of fuel, and to calculate that, we need a delta V budget, which is the total change in velocity from all the maneuvers we perform along the way. And of course, after launching your payload into space, you'd like to check in on it. You need to communicate, and for that, we need to know the link budget of a mission. And of course, it would be nice to know how likely it is for your multi-million-dollar spacecraft to crash into something, particularly when that thing is someone else's multi-million-dollar spacecraft. And spaceflight necessarily involves a lot of testing in prod, but without mission simulators, each launch would be equivalent to sort of sticking your finger in the air and saying, that way. Here we see, on the right, Ferris has identified, thanks to simulation, a critical vulnerability in plans for the galaxy's most ambitious, expensive orbital death machine, giving his employer the opportunity to correct the design before it goes to build. But we've all seen the documentary, Star Wars Episode 4, A New Hope. We know how it ends, and this is because Ferris works for Boeing. Now, I keep saying next generation, and not entirely for the Star Trek pun. Space has changed dramatically in the last decade. Private enterprise has sort of muscled into the ring, and the prize right now is real estate in low Earth orbit. Now, ask any billionaire. Super yachts, very 2015. When Musk and Bezos get together to assert their masculinity, they flop it out all onto the table and compare the size of their satellite constellations. Networks of satellites flying in unison, communicating, providing global coverage at a fraction of the latencies achievable with traditional geostationary orbits. And that is a lot of satellites, and it is getting crowded up there. The image here depicts the spacecraft, rocket bodies, and the debris that was big enough to be worth naming in low Earth orbit alone. And since the number of safe orbits is limited, we essentially have a gold rush in which it is extremely difficult for smaller players to compete. So if we value open access to space for the future, then high quality, free, open source software is a critical piece of that puzzle. Commercial mission simulators are hugely expensive, like less than a rocket launch, but you'll want a mortgage, not a credit card. Now, meanwhile, existing open source solutions have tended not to keep pace with the changing nature of space missions. For example, space junk is a massive problem. The image on the right here is the debris that is big enough to track, but not worth naming. And this is just trash doing 18,000 miles an hour. Right? Cleaning that up is a whole new class of mission. And another example, one of the sponsors of RustConf this year, K2 Space, is redesigning how we send mega-class satellites into space. And support for missions like these has to be custom built, and that carries substantial development costs. And a typical mission analyst works at a much higher level of abstraction than an astrodynamics library. This is the Python crowd. The people planning the missions are very rarely the same people extending the simulator, and startups must be able to afford both. And even if they can afford both, combining old tools in new and exciting ways results in new and frustrating failure modes. Like there is, in fact, a 10th circle of hell in which people call Java astrodynamics routines from MATLAB and try to debug the results. I have done it. I won't do it again. You cannot make me. So what makes Rust a better backend for a modern space mission simulator? Well, it's fast, obviously, we know that. Python-based implementations like Polyastro, I think is the most famous example, tend to struggle with complex trajectory calculations or propagating large numbers of orbits. But Rust doesn't rule out Python for users who want a bit more control in a language that they are familiar with. LOX uses Pyo3 to expose Python bindings behind a feature flag. And native compilation and portability are also highly desirable. So NASA's free simulator, GMAT, just doesn't run on Apple Silicon. The latest stable build dates to 2016. And Orikit, the most successful open astrodynamics project to date, is written in Java. So like it or not, like a facehugger, the JVM is coming along for the ride. Most importantly, though, at least from my perspective, Rust is expressive. Rust is phenomenally good at modeling hardcore domain concepts in a way that non-specialist developers can understand. And that is the lifeblood of maintainable open source projects. And to prove that to you, we are going to do a bit of domain modeling. Starting from a philosophical question, we are going to build up the real prime-time abstractions that underpin the LOX time crate. So, a gentle warm-up question before we stare directly into the time vortex. What is time? What is time? Well, true. I wish. That's a U8. That would be beautiful. But I have a web development background. So as far as I'm concerned, time began on the 1st of January, 1970. And it's been going up in nanoseconds ever since. And if you take this view of the universe, time fits very nicely inside an I-64. But there's two opposing problems with this model in the context of a space mission simulator. On the one hand, I-64 is too small. That's 18 quintillion nanoseconds, which sounds like a lot, but it's about plus or minus 300 years. And that might not be long enough to get those astronauts back from the International Space Station, but it should be long enough for most space missions. It's not enough for most or some space algorithms, though, because astronomers don't use the Unix epoch. Mostly, they use J2000, which began midday, January 1st, 2000. But the Julian epoch is also used, and that began 4713 BC. And a qualified astrophysicist will tell you that that is more than 300 years ago. On the other hand, a nanosecond is a long time in space. Where we have algorithms that are accurate to fractions of nanoseconds, we would like to be able to represent their output correctly. And we should avoid snowballing rounding errors, since operations like orbit propagation are effectively pipelines of state calculations, where the outputs of one stage in the process become the inputs to the next iteration. So how do we improve on an I64 representation of time? Well, we can try first to stand on the shoulders of giants and take inspiration from a time representation used by the International Astronomical Union's Standards of Fundamental Astronomy, or SOFA for short. And this is a collection of essential astronomy routines written in C and Fortran 77. Fortran, if you don't know, is like catnip to physicists. They can neither have nor want nice things. I couldn't tell you why. So we're going to look at the SOFA C representation. And it's two doubles. Just straight up, two doubles. The time relative to some epoch, usually J2000, is represented as the sum of two 64-bit floating point numbers. How do you apportion the time between these two doubles, you ask? With great care, because this is C, where the behavior of your code depends on how well you read the instruction manual and how much you had to drink the night before. The larger the integral part of each double, the fewer decimal places of precision your time supports. There is a correct way to reliably achieve femtoseconds, 10 to the negative 15 precision, but if you're not up to date on your IEEE 754 floating point arithmetic, how precise your time is depends on what your time is. Chef's kiss. There is value here, though. There is value, and with a bit of type-driven Rust, we can codify the good ideas and prevent users from cutting themselves on the sharp edges. First, we take one of those doubles and restrict it to an integral number of seconds relative to J2000. An I64 might not give us enough nanoseconds to play with, but it fits an order of magnitude more seconds than the age of the known universe. And that leaves us to model the fraction of the current seconds. And with LOX, we initially tried using another I64 to count attoseconds since the previous second. But in practice, floating point arithmetic is so fundamental to physics that we'd have increased the complexity of the code massively while decreasing performance. A mission simulation isn't actually concerned with anything happening at the attosecond level. An F64 subsecond, on the other hand, integrates very nicely with established algorithms. But rather than use it raw, we define a sub-second new type to enforce the invariant that an F64 must be in the half-open range 0 to 1. And by restricting an F64 to the subnormal numbers, we guarantee that our time is always at least precise to 15 decimal places, and that's femtoseconds. So, easy, right? A type-safe, user-proof time representation. Except it doesn't work. Or rather, it's not enough because there is one thing to ruin it all. UTC. Or as I've come to know it, the devil's time scale. It cannot be unambiguously represented as a monotonic counter. UTC is an unholy hybrid of International Atomic Time, or TIE, and an average of the world, and TIE is an average of the world's most expensive atomic clocks. And that's combined with solar time, UT1, which is based on the Earth's rotation, which changes. So UTC is kept within plus or minus 0.9 seconds of UT1 by the inclusion of leap seconds, which I'm sure you're all familiar with. And these are decided about 6 months in advance by the International Earth Rotation and Systems Service, who have the best Christmas parties. If I give you the time 536,500,836 seconds since J2000, are we at midnight on the 1st of January 2017, or 23:59:60 during the leap second of December 31st, 2016? And I do say inclusion of leap seconds, not addition of leap seconds, because leap seconds are allowed to be negative. They have never been so far, but they can be. And the reason for that is that the speed of the Earth's rotation changes over time. Since UTC was introduced in 1960, it has tended to slow, causing us to add leap seconds to avoid UTC getting too far ahead of UT1. Since 2020, however, the Earth has been spinning a bit faster. And if that trend continues, well, good luck being on call for the negative leap second. And UTC is just the tip of the iceberg. Astronomers work with time in a minimum of 7 timescales, a minimum, from good old atomic time to TDB, which is based on a hypothetical clock moving with the solar system's center of mass and accounting for time dilation. Now, on this slide, you'll also see that Coro, the unsafe rust urchin, is marking the two extra fun timescales that cannot be determined without external observational data. And LOX has to model all of these and transform between them in an ergonomic, intuitive way. So let's start with the representation of the timescale itself. Luckily, every timescale that isn't UTC is guaranteed to increase monotonically. So our base time representation with an I64 second and an F64 subsecond is sound. We just need to pair this indicator with some form of time scale. So we initially tried representing timescales as enum variants. And at first glance, an enum seems like a good fit because the number of variants is fixed and it wouldn't require any special treatment when mapping to Python. But we can't specify bounds on enums like we do with traits. We can't define a function that accepts only a tie variant of the timescale enum, for example, and different algorithms have inputs and outputs in different timescales. Instead, we define a timescale marker trait and implement it for dedicated zero-sized structs for each timescale. With timescale as our trait bound, we can implement a generic time type that combines a delta since an epoch plus a scale. And since each timescale is zero-sized, it takes no more space than the raw timestamp, which might lead you to ask if the scale field couldn't just be phantom data. Maybe Einstein was wrong. Let's entertain that idea for a second. What if time isn't physical reality, but just a figment of the compiler's imagination? Unfortunately not. Nature works in mysterious ways, and Python is a dynamic language, so Python bindings cannot be generic. By retaining the scale field, we preserve the ability to instantiate times dynamically using some enum-based smoke and mirrors that unfortunately I don't have time to go into. But if you don't need Python, rest easy in the knowledge that this field weighs nothing. Back in the land of shadows, however, we made the decision early that although we can't cast UTC into the fire, we can contain it. So UTC gets a dedicated year, month, day, hour, minute, second, subsecond type, which exists at the boundaries of the LOX time crate. It is treated strictly as a human-readable I/O time format, which must be converted to a continuous time for use in calculations. Flight dynamics engineers expect input times in a format they understand, which is a very reasonable expectation of a very unreasonable time scale. So we do significant legwork to hide that complexity from the user. The UTC type is leap second aware and ensures that each transformation to other scales is unambiguous. We achieve that through the leap second provider trait, and LOX provides a default implementation, which I wrote and experience violent flashbacks to this day. We don't have time to get into the implementation, but I will be taking questions on Discord afterwards, so feel free to ask me those questions there. Next slide, please. I think the battery is dead. Hey! So how do we specify timescale transformations. The graph on the right shows how each timescale maps to the others, and some of these appear to have very little in common. Pi to TT, my absolute favorite, just adds 32.184 seconds. And this is the kind of simplicity I live for. Meanwhile, TT to TCG, that's a linear transformation. But the next edge, TCG to TDB, is a four-dimensional transformation. More complex, certainly, but this data can be specified statically and compiled into your binary. However, as we already know, conversions involving UTC need historical and upcoming leap-second data. And UT1, being solar time, isn't technically a time at all, but the orientation of the Earth with regard to the sun. This means we need a current source of Earth orientation parameters based on observed data. And library users should have the option to provide their own data. So given our stated goal of an ergonomic and intuitive API for astronomical time, this appears to suck. How can we provide a high-level interface that is convenient call with whatever timestamp the user has to hand without creating a mess of speculative dependencies for unrelated transformations? If we squint, though, we can just about make out a homogeneous set of timescale transformations. And with Rust, we can fluently articulate this relationship in code. So try to scale is the base trait underlying all of LOX's timescale transformations. And it is supremely pessimistic. It assumes that every timescale pair requires a data source in the form of an offset provider, and that offset provider is fallible. So try-to-scale doesn't care that tie to TT is simple addition. It is a hammer, and every transformation is a nail. We know better, of course. Most transformations, constant, linear, or four-dimensional, are infallible, and the first step on our journey from blunt instrument to keen edge is to implement offset provider for no-op offset provider, a zero-size struct that does nothing without fail. And this starts the process of progressive trait specialization, where each tightening of the trait bounds exposes a more convenient but more situational subset of timescale transformations. We define to-scale, bounded by an infallible try-to-scale based on no-op offset provider. We don't want to force callers to handle failures that cannot happen. And even better, we can blanket implement to scale for any type that implements an infallible try-to-scale, saving the maintainers the headache of doing it manually. Thank you, Rust. This process continues all the way down to the level of single-scale transformations. Traits to tie, to TT, and so on specify zero-argument, infallible methods with default implementations for all pairs of simple transformations. But what about the fallible ones? You've already seen leap seconds provider in our discussion of UTC, and leap seconds provider is in fact a specialization of offset provider. And we do the same thing for the UT1 tie pairing, which depends on data derived from observed Earth orientation parameters. Delta UT1 tie provider is a specialization of offset provider, and try to UT1 is a specialization of try to scale over a delta UT1 tie provider. There are no to UT1 or to UTC traits because they are fundamentally fallible operations. Putting it all together, and we have a collection of traits that allows LOX and third-party users of the LOX time crate extraordinary flexibility to design types and call signatures based not just on the concrete timescales that a particular algorithm requires, but on the graph of timescale transformations. Rather than give me tie, we can say, give me any infallible path to tie. You can say, give me a path to UT1 and the observed data to traverse it, or you can say, I have observed data, give me the path that consumes it. And that is how you model all of time in Rust. Now, thank you so much for listening. You can find LOX on GitHub at the link in this at the end of this description. It's available under the Mozilla public license. It is not V1 yet. It is not yet on Crates.io because there is some ESA bureaucracy to iron out. But for the YouTube crowd, I will bat my eyelids at the organizers and ask them to put a link to these slides in the description. You can find more of my work at howtocodeit.com or reach out to me directly at angus@howtocodeit.com. I'll be very happy to answer any questions you have. I will also be taking questions on Discord after the talk, but please remember, I am not an astrophysicist. If you ask me questions that stray too far from the rust of it all, I reserve the right not to publicly embarrass myself. Thank you very much.